Hello everyone, I am Uttam Satpute, Professor Electrical Engineering Department at Dr. D.Y. Patil Pratishthan's College of Engineering, Nagar, Kolhapur. So welcome to this video on course Power System Stability and Control, and in this video we shall deal with Unit 2 Power System Stability Numericals. So this is numerical number 6 from the question bank. Now let us uh, see the question. What a 50 Hz two-pole turbo alternator rated 30 MVA, 11 kV has an inertia constant of H is equal to 7 megawatt second per MVA. Find the acceleration if, now this is, please correct, if the input rotational losses is 24,900 HP and electrical power developed is 15 megawatt minus losses. So let us first write down what is given in the problem. So we are given one alternator, turbo alternator. It is 50 Hertz. P, it is two-pole machine, and its rating G, we write it as G 30 MVA. Voltage 11 kV. Inertia constant H is equal to 7. Now we have to find the acceleration. So let us write what is acceleration. So I will write in terms of our swing equation d square delta divided by dt square. This will give us the acceleration of the synchronous machine if there is an imbalance between the mechanical input and the electrical output. Now the C part we have to find out now what is the relation between what is given and what is asked. So this is what is asked. Now we have a swing equation. So I will use the swing equation that relates what is given and what is asked. The swing equation is G H divided by 180 F d square delta divided by dt square equal to Pm minus P, and this is in megawatt. Okay, so this is what the equation we have already learned. Now in this equation, let us first calculate this part. So this is what we call it as yam. So can be another moment of inertia yam, which is equal to g h divided by 180 into f. So g into h, you substitute the value. Uh, now g, it is given as 30, the rating of the machine. H is given as 7, inertia constant of the machine, divided by 180 into frequency is given as 50 Hz. So this value will come out to be 0.023. The unit is megawatt second square per electrical radian. This is uh, electrical. This is in radians. This is mechanical radians because we have taken here 180. If we would have taken pi, then our unit would have been megawatt second square electrical radians. Okay. Now let us calculate Pm. Pm is a mechanical input given. Now the mechanical input, what it is given, it is in HP. So we have to convert it into megawatt. So already here it is in megawatt. So 24,900, we already know 1 HP to 735.5 watt divided by, to convert into megawatt, so I will make it 10 raised to 6. So this will come out to be 18.31 megawatt, and P, it is given that the electrical output is 15 megawatt. So using the equation now, D delta equal to 18.31 PM value minus P value is given as 15 divided by M. Now here it is, we have calculated 0.023. So if we calculate this value, it will come around 143.91. This is mechanical radians per second square. So this is what I have if there is an imbalance between the mechanical input and the electrical output. So this is the solution for the question number 6. Now let us come to question number 7. Now let us write first what all of things are given. Uh, Now we are given one power station, there is one power plant, one power station, and in this power station we have 4 generators. So 1, 2, 3, and 4. These are all generators in this plant. So this is plant number 1, and each set has 80 MVA generator. So each generator, it is 80 MVA and having an inertia constant. So this is, I will call it as G1. Okay, so G1, G2, G3 and all. So G1, and H1, it is equal to given as 7. The inertia constant of all the units of generator of power plant 1. Now there is another power plant, plant number 2, and it has 3 uh, generators. Each rated, I will call it as G2, which is 200, and H2 inertia constant, it is given as 3 megajoules per inch. The stations are located close to together to be regarded as single equivalent machine for stability. Calculate the inertia constant of equivalent machine on 100 MVA. So what you have to do now, they are connected in parallel and they are very close. So in stability study, what we do, here we have 4 generators and here we have 3 generators, and all they are swinging together. So all the generators, their inertia can be combined and can be given by one equivalent inertia. So the equation is H equivalent, it is equal to, now let us calculate the, now because they are of different ratings, we have to convert all the inertias on common base. So common base, it is given as 100 MVA. So G system, I'll call it as G system, which is equal to 100 MVA. So the formula I can use here, it is G1 into H1 divided by G system. So this is the equivalent inertia, or this is the inertia of generator H1 on system base, but we have such 4 multiplied by 4 plus G2 into H2 divided by G system, and in plant 2 we have 3 units, so I will multiply it by 3. So substituting all the values, G1 is 80 into 7 divided by 100 into 4 plus 200 into 3 by 100 into 3. So we get to this value equivalent to be 40.4 megajoules per MVA. Please verify this answer. So this is what is the equivalent inertia of all the generators. So in the stability study, all these 7 generators, they can be replaced by one generator. The inertia constant is equivalent to 40.4 megajoules per minute. Okay. Then we have another problem. This is question number 8. Let us write down what all things are given, what is asked. So what all given here? Uh, Frequency, we have a generator and frequency is 50 hertz and it has 4 pole machine. Rating of the generator is given as 100 MVA. Voltage is given as 11 kV and inertia constant H, it is given as 10 megajoules per MVA. Now what is asked? So this is given. We can divide the problem into what is given, what is asked. Now what is asked? The first one is stored energy. They have asked one A part is stored, and second part they have asked the acceleration. So the acceleration, as we know, it is d delta dt square. So this is the acceleration asked. Now how you relate given and what is asked? So let us first find out energy stored. So C part I will write it as energy stored or stored energy equal to the formula already we know, it is G into H. So G is given as 100 into 10. H is given as 10. So this is equal to 100, so 1000 megajoules. So this is the energy stored in the rotor. And the second part they have asked D. So I will use the swing equation for this second part, acceleration. For acceleration, we will use the swing equation d square delta divided by dt square equal to Pm minus P. Okay. So let us first calculate m value. M is equal to, already in the previous problem I have given GH divided by 180 into F. So G is given as, already given, the rating of the machine 100 into 10 divided by 180, the frequency. So this will give you the value as point 0.11, 0.11. The unit is megawatt, second square divided by radians, electrical radians, mechanical, this angular, sorry, radians. Okay. Now I will calculate over here. Now we have to calculate the delta d square delta by dt square equal to Pm value is given here, which is 125 megawatt. Okay. So 125 minus 50, sorry, 75 divided by m value. So 0.11. So this value come out to be 454.45 uh, mechanical radian per second square. So mechanical radian per second square. So this you can refer, here we have calculated the stored energy and the acceleration if there is an imbalance between mechanical input and electrical output. Then the next, the last problem in this video, so solution. Now this is a similar problem as we have in the seventh problem. We have asked the inertia constant. So we are given two units now. This is unit 1 here and it is G1. I will call it as G1. It is 500 MVA, and H is given as 5 megajoules per. Now there are some other parameters. There are some other data given which are irrelevant, and there is another unit whose rating G2. It is 800, and the inertia constant is 4 megajoules. Okay, and they are connected in parallel. It means that they are swinging together. And now we have to calculate inertia of the two machines. So it is given by equation G1 into H1 divided by G system. Now G system here we have given a system base. What we have to choose? It is given as 200. Okay, and plus G2 into H2 divided by G system 2. So G1 is given as 500 in inertia constant divided by 200 plus G2, it is given as 800 into 4 divided by 200. If you calculate this value, it comes around 28.5 megajoules per MU. So this is the equivalent inertia of two machines connected in parallel. Okay, so in this video, I have solved all the numerical which are there. Thank you very much.